How did the solar system form? It's important to remember at the outset that this is historical science. Nobody was there at the beginning of the Earth and the planets and the Sun, so we don't know for sure, and we may never know for sure exactly how it happened. But scientists have ideas, and there is evidence that survives from near the origin. We're trying to describe the properties of the solar system as we see it now in terms of how it formed and how it got the way it is. Because we know about the planets in essentially gory detail, we have to take a middle view of the solar system. We want to explain the broad features without getting obsessed on the details, which may be hard to explain. So scientists look for commonalities in the way the planets behave and the way they're situated, and try and draw out a general principle behind those properties, while acknowledging that there will be peculiarities that they may or may not be able to explain. In general terms, the orbits in the solar system are quite regular. The planets orbit the Sun in the same direction that the Sun itself rotates. And most of those planets also spin in that same direction. In terms of angular momentum, the angular momentum vectors are aligned. Another common feature is that the interior of the solar system, the terrestrial planets, are small and rocky, while the four outer giant planets are gaseous and composed mostly of hydrogen and helium. Beyond the Sun and the 8 major planets, there are swarms of interplanetary objects and debris. There are asteroids between the orbits of 2 of the planets, and similar-sized rocky bodies beyond the orbits of the outer planets. All of these are aligned in a plane, and most of the objects in the solar system occupy that plane. There is also, however, a nearly spherical cloud of comets, which go far beyond the orbits of the outermost planets and travel on elliptical orbits into the inner solar system. Finally, there are exceptions to the general rules. These exceptions may or may not be important. An exception to the rotation rule is Venus, which is counter-rotating or spinning in the opposite direction to all the other planets as they all orbit the Sun the same way. Uranus, an outer planet, has a spin axis that's tilted on its side, or an inclination of nearly 90 degrees. The Earth-Moon system is an exception too, because the Moon is by far the largest satellite of a planet compared to the planet size in the entire solar system. We need to understand whether these exceptions are telling us something important about how our solar system and solar systems in general work, or whether it's just happenstance. The first question that we can confidently answer is, why are there 2 types of planets when they all formed out of the same cloud of gas and dust? The general scenario here is that a nearly spherical cloud of diffuse gas and dust, initially much larger than the solar system that eventually forms, has a small amount of rotation. That's reasonable. Most gas clouds in the interstellar medium or in the galaxy will have a small net amount of rotation. As the cloud collapses, perhaps triggered by a gravitational event nearby like a dying star, it collapses faster along the spin axis direction than along the equator, naturally forming a disk. Conservation of angular momentum says that as it collapses, the objects in it and the gas itself will spin faster. What happens next depends on the temperature created by the young Sun. The young Sun was brighter and more luminous than it is now. In its first few 100,000 years, it was actually 10 or 20 times more luminous as it went through what's called a T-Tauri phase. This young Sun and its strong UV radiation drove away gas from what is now the inner solar system, leaving the planets that formed to be pure and naked rocky cores. But in the outer solar system, the radiation was insufficient to drive away all the gas. Temperatures were cooler, and there was more gas there in the first place, and so a similar number of rocky cores were able over time to accrete mantles of hydrogen and helium gas. Remember, the planets are made of what the Sun is made of overall. The gas giants mostly hydrogen and helium, which is what the Sun is made of, 99.9% of its mass. The rocky cores are negligible in mass. If you sweep up all the rocky objects in the solar system, the terrestrial planets and the cores of the giant planets, all the asteroids, all the comets, and put them in a pile, they'd be less than 0.1% of the mass of the Sun. So all the interesting things that happen at the periphery of the newly formed star are small components of the total mass. What kind of materials form from this condensing gas and dust is determined by simple radiation physics. In the early solar system, with this luminous Sun, it's possible to calculate what the temperature is at any distance from the star. So you can calculate at what distance rock would be molten or solid, and at what distance something like water would be a liquid or frozen. The major demarcation in the young solar system is something called the frost line. Inside the frost line, water and similar gassy elements called volatiles, such as carbon dioxide and methane, can be either liquid or gaseous. Beyond the frost line, or further from the star, these materials are solid or frozen. So we can imagine and expect that the solar system will have an outer region filled with icy rocks and an inner region where there are still rocks, but any liquids present are in the liquid form or perhaps gaseous. What about the moons of the giant planets? We now know that each of the 4 gas giants has moons around it, dozens in the case of Jupiter and Saturn. And we think these planet-moon systems formed in a miniaturized version of what happened in the solar system as a whole. The gas cloud where the giant planet would form collapses along its equator, forms a disk, and out of the disk moons coagulate by accretion, by pure gravity processes. Those moons are spinning and rotating in the same direction as the planet rotates, and it's a harmonious set of motions, similar to what is seen on the solar system on a larger scale. It's difficult to make a computer simulation of the formation of the solar system, but if we look at one, we can see the main features of this story, where the infant sun drives away the gas from the inner solar system, leaving rocky cores, and the outer solar system is able to build giant planets from the hydrogen and helium left over.
5 billion years ago, a cloud of hot swirling dust and hydrogen gas gives birth to our sun and planets. As the cloud spins and collapses inward, it flattens into a central mass and surrounding disk. Dust and gases in the disk form other smaller condensations, each spinning about its own center. Gravitational condensation heats the central mass, density increases dramatically, and fusion begins. Energy is released and our sun flares into existence. The solar wind of the newly ignited sun blows away leftover dust and gas in the vicinity of the inner condensations, leaving the rocky inner planets, Mercury, Venus, Earth, and Mars. In the outer reaches of the disk, the solar wind is weaker. The remaining dust and gas condense into the large gaseous planets Jupiter, Saturn, Uranus, and Neptune. This scenario leaves us with many questions. How does this process begin in an initially homogeneous cloud of dust and gas? If it happened here, could it happen elsewhere? One challenge for planetary scientists is to find evidence to answer these and other questions about the solar system.
In the standard theory of how the solar system formed, the giant planets form because it's cooler and there's more material in the outer solar system for the rocky cores to accrete large mantles of gaseous hydrogen and helium. But in the inner solar system, the terrestrial planets, which are quite close to the sun, have the gas that remains driven off by the radiation from the young, bright, luminous sun, leaving just the rocky cores. Now, the existence of rocky cores in the giant planets is a matter of inference and speculation, because nobody's seen these rocky cores directly, but we're fairly confident that they exist. Those are the general patterns and rules, but what about the exceptions? The exceptions are interesting. Perhaps the most interesting exception is Earth's large moon. We know Earth's large moon plays a significant role in tides and in stabilizing the Earth's tilt and orbit. Some people even speculate that the existence of the moon in its large size has played a role in the Earth being a habitable planet. So it's important to know if Earth's large moon is a freak of nature or something that could happen more often. The story that's told about the moon is a particular story involving the impact of the infant Earth with a large object the size of Mars. In this idea, the moon was splashed off when the rock was almost molten to form an orbiting object that became a satellite. This theory is designed to explain some anomalies in terms of the moon relative to other objects of similar size in the solar system. It's been known for decades that the moon has a very weak magnetic field, which means that it has almost no metallic core. Earth, on the other hand, has a strong magnetic field due to an iron-nickel core that's quite substantial. So we need to understand why the moon has no metallic core, when moons and planets all essentially form from the same material. The large size of the moon, its close orbit around the Earth, and its particular material, essentially mantle material, is all explained by the impact hypothesis for the moon's formation. It's speculated that this happened within 10 or 15 million years after the Earth formed. The two objects almost formed at the same time 4.5 billion years ago. The evidence for the impact hypothesis is fairly direct because it comes from the 450 plus kilos of rocks that were returned to the Earth by the Apollo astronauts. We've looked at these rocks in gory detail, and their chemical abundances and mineralogy is very similar to Earth mantle material, making it quite plausible that the moon was formed from the Earth's mantle splashed off into space and then condensing into a large satellite. If an impact happened here, maybe it happened elsewhere. So this idea has been extended to explain why Venus counter-rotates, or spins in the opposite direction to all the other planets, and why Uranus is tilted on its side. By inference, both of these were the result of impacts too, but in those cases there's no direct evidence, and it's just a story that's consistent with the data. We may never be able to prove that impacts caused those strange orbital properties. Computer simulations have been important in affirming the idea of the impact hypothesis for the moon's formation, and in showing what the impact might have been like that left the Earth and the moon with the angular momentum they have today. Again, this does not prove the hypothesis, but means it's the most likely scenario for how the moon formed.
In this computer simulation, an object with a mass slightly larger than Mars strikes the early Earth with a relatively low angular momentum and is drawn out into a bar. Rock is concentrated in the inner and outer thirds, with iron in the middle third. From the bar, all of the iron from the impactor falls rapidly through the mantle to wrap around the core of the proto-Earth. The remaining outer rock from the bar misses Earth and goes into orbit. Material continues to peel off. Some of it strikes Earth while angular momentum puts the remainder into orbit. In some cases, a disk of material may form. In this calculation, a large clump that has 85% the mass of the moon remains. Material near the clump strikes it and sticks. The moon may have formed in this way. In the case seen here, both Earth and the impactor had iron cores and rock mantles.
The formation of the solar system 4.5 billion years ago is historical science. We may never have firm evidence on how it happened. But there's a general hypothesis that all the planets formed out of the same collapsing, rotating cloud of gas and dust. The inner planets forming rocky cores where most of the gas remaining was driven off by the radiation from the young sun, and the outer planets cooler with more material able to steadily grow mantles of hydrogen and helium by gravitational accretion. There are general patterns in how the solar system behaves in terms of orbits, but there are exceptions too. Some of the exceptions are attributed to impacts in the early violent days of the solar system.